Okay. So, I'm going to get started. I've got attendance for everybody. Most people are online, but so, announcement. Chapter 17 homework is due on the 25th. The chapter 17 quiz will be on the 25th of this Friday in SI. The chapter 18 homework and chapter 18 quiz are due on 29th. That's Tuesday next week. So we're going to have a quiz in here during lecture. So you need to be here for that on Tuesday. And on Thursday next week, the 1st, we're going to have the third exam on chapters 16, 17, and 18. The Eclipse lab is due today. If you haven't already turned it in, most of you have already turned it in. And the labs today and next week are for makeups. And if you have any late labs, please turn them in. If you have any late labs that you find when I'm not around, you can, not during class time, you can drop them off with me. If you're ready, I'm usually around here, or you can always drop them off outside my office, which is room 335 down at the end of this hallway. So, continuing on with chapter 18, we talked about stars having a luminosity and how we can figure out their luminosity if we know their distance and their apparent brightness. And we can get their absolute magnitude. If you plot absolute magnitude versus temperature of the photosphere for stars, you find that most stars become brighter as they get hotter, and they form a narrow diagonal band in this diagram that's called the main sequence. The hottest and generally brightest stars are blue. They're also on the main sequence, the largest star. The coolest and generally least bright stars are red. These are the smallest ones. And we can measure their mass using various techniques. We find big, heavy stars are large, blue, short-lived. Small, light stars are dim, red, long-lived. So that's the major. This diagram was put together by Hertzberg and Russell. It's called the HR diagram. And this is a short video about it.
When looking up at the night sky, you can be forgiven for thinking that all the stars look similar, but each one has its own unique properties. From Earth, there are two easily observable and measurable stellar features, brightness and colour. But plotting these two properties of stars on their own doesn't really show anything, as observable brightness is affected by another crucial factor, stellar distance. In other words, even though one star may appear dimmer than another, it could actually be brighter, but just further away. When astronomers realised that they should take stellar distance into account, they were able to work out the actual or true brightness of stars. The Hertzsprung-Russell or HR diagram is named after the two discovering astronomers who used observational data to create a graph to classify and study the evolution of all stars. They labelled one axis of the graph with absolute magnitude, or true brightness of the star, and the other axis with colour, which is linked to the temperature of a star and defines its spectral type. Stars begin their lives in large, dark, cool clouds of gas and dust called nebulae. Pockets within these nebulae can begin to contract, getting smaller, denser, hotter and brighter. These cores are known as protostars. A protostar with too little mass would be too cool and dim, and it will never become a star. And an excessively massive, hot and bright protostar would be too unstable. But if they have just the right mass and temperature, they begin to fuse the hydrogen gas into helium, and a star is born. Each star that is formed will take its appropriate place on the main sequence of the HR diagram, While they fuse hydrogen in their cores, stars spend their life on the main sequence. Like the majority of stars, our Sun is a main sequence star. But when it runs out of its fuel, hydrogen, it will evolve off the main sequence, and as the Sun's hydrogen-fused core collapses, it will reignite and fuse the helium in its core into carbon and oxygen. Its surface will expand and get cooler, and the Sun will turn into a red giant star. As the helium in the core is exhausted, the Sun will evolve into a planetary nebula, blowing off its outer layers, leaving behind a small, hot, white dwarf star that is rich in carbon and oxygen. Stars that are more massive than our Sun fuse their fuel more quickly and evolve off the main sequence to become red supergiant stars. These supergiants are able to fuse even heavier elements in their cores. When they run out of all their fuel, they end their lives in a supernova, leaving behind a very hot but small neutron star or a black hole. So thanks to the work of Hertzsprung and Russell, astronomers can now work out where a star is in its evolution if they know its true brightness and temperature.
So this is the Hertzsprung-Russell diagram. It's traditionally drawn with higher temperatures on the left and lower temperatures on the right, because the original version was measuring something that corresponded inversely to temperature. I don't remember exactly. It was some strength of some ionic line or something in the spectrum. And then the luminosity, the brightness. And these are in scale of the luminosity of the Sun. And most stars end up on this main sequence here. 90% of the stars in the sky are on this main sequence. And that is actually because 90% of the star's lifespan is spent sitting on the main sequence, fusing hydrogen into helium. It's when they run out of hydrogen in their core that they'll leave the main sequence, become a giant or supergiant, depending on how big they were. And then after that, the really big stars will explode in supernovas. More medium-sized stars like our Sun will throw off their outer layers in a planetary nebula and leave behind a white dwarf. And we find white dwarfs down here, and white dwarfs still glow because they're very hot, but they're very small. They're physically like the size of the Earth per scale, roughly. And they can be up to about 1.4 solar masses. They're very dense, very hot balls, and they just are slowly cooling and glowing. So several types of stars are not on the main sequence. So the main sequence is where most stars are when they live most of their lifespan. There are red giants, which are very large stars that are cool yet still very bright. And the very brightest of these are called red supergiants. These are huge stars. So red giants, their surface is relatively cool, but they're really, really big, so they put off a lot of light. And white dwarfs are stars that are very hot, yet are dim due to their small size. White dwarfs are very small, but we can still see them because they're incredibly hot. And that's because they're the cores of exploded stars that have collapsed. And so are these compact, super hot, super dense things. And when we do spectral analysis of the stars, we find that even the most distant stars contain the same elements we find in our solar system. Actually, right now, that's one of the things that's being discovered with new observations with the James Webb Space Telescope, is that we're finding stars that look a lot like modern stars much sooner than we thought in the history of the universe. However, there are variations in the spectra that depend on the temperature of the individual star's photosphere. Basically, different spectral lines get excited or emphasized depending on the temperature. So the pattern of the absorption lines in the spectra can be used to determine both the composition of the star and its surface temperature. And that's really useful because that allows us to correct for things like redshift and other things that could change the color of the star. So you can have situations where, like, if there's dust in the way, it scatters away more blue light than red light, things like that. But looking at the spectral lines is independent of that. And so the stars have been placed into 7 spectral classes. The letters seem kind of random. That's because the original set of classes was based off the strength of a particular line in the spectrum. And that strength the strength of that line doesn't necessarily correspond to, like, it's strongest at like a temperature in the middle, for example. So these are O, B, A, F, G, K, and M. You can see them on top of the diagram here. O stars are the hottest. Then B, A, F, G. Our sun is a G-type star. K and M. M stars are the dimmest, are the coolest, lowest temperature stars. So our sun falls relatively close to the middle of the sequence. It's a class G star. Sirius, for example, is quite a bit hotter than our sun. It's a class A star. And astronomers have found that the majority of the stars are small out there, are small, cool class M stars called red dwarfs. So the closest star to Earth besides our sun is Proxima Centauri, and it's a red dwarf or a class M star. Oops, I have to hide those announcements. So in between the stars is the interstellar medium. It's the gases and dust that's distributed among the stars. These are about 75% hydrogen, 25% helium, and a trace amount of heavier elements. And you're going to find that 75% hydrogen, 25% helium all over the place. And that's because that is sort of the starting material of the universe. During the Big Bang, fusion occurred and formed about 75% hydrogen, 25% helium. So the dust, which is only about 1% of the interstellar medium, is primarily carbon, iron, oxygen, and silicon. So sooty stuff, iron, and then silicons, like so. And the particles are about the size of particles in smoke. Some of them are sooty-like, some of them are sand-like. So yeah, here's a clip about interstellar space. And the one thing you need to really understand is that space is really empty. It's very thin, which leads to some very strange effects.
Interstellar space is the space between the stars. But that doesn't mean that all space is interstellar. It's a bit more complicated than that.
At the center of the solar system is our very own star, the Sun. That has 8 planets orbiting around it, including our own. And the Sun is also constantly spewing out a stream of high-energy particles, which we call the solar wind. This wind forms a giant bubble around our entire solar system. Other stars have similar shells around them. Interstellar space begins at the edge of those star bubbles, which are much bigger than these bubbles.
Interstellar space is hot and cold at the same time. The particles are moving really fast. Fast-moving particles means high temperatures. But get this, you can still freeze to death. The particles are so spread out that they're not very good at transferring heat to your body.
Inside the solar system, all of the wind comes from the Sun, and the Sun's bubble actually blocks out the wind from other stars. But out in interstellar space, there's wind blowing from many different stars, and it all swirls together. It's a glorious mix of particles, energy, and magnetic fields, totally unlike the kind of environment we experience on Earth.
In the 1970s, NASA launched 2 space probes that are now speeding through interstellar space, beyond the bubble of our solar system. After a tour of our neighbor planets, Voyager 1 and Voyager 2 are now the first human-made objects on an interstellar adventure. Another out-of-this-world thing about interstellar space is that each of the Voyagers is carrying a golden record on its journey with songs, sounds, and greetings from our home on planet Earth. So maybe one day they'll tell the story of our world to extraterrestrials.
It's pretty cool that we humans now have a message in a bottle all the way out there in interstellar space. Thanks for joining us with 5 things about interstellar space. And tune in to NASA Science Live for more about interstellar space.
Okay. Now, the gas and dust in interstellar space is not distributed evenly. There are places where it's thinner. Actually, we're in a bit of a bubble. Like the sun is located in an area that's actually a thinner part of interstellar space. And there are also places where that gas and dust is concentrated. And we can see these as nebulae. Nebulae are concentrations of cool, dense clouds of gas and dust that are observable. And there are 2 main types. There are bright nebulae and dark nebulae. Dark nebulae block light coming from behind them. Bright nebulae are lit up by something, reflecting light from something. And they're called nebulae because they look like clouds. And that's what that word means in Latin. So here is a short video about images of nebula.
Thanks to Squarespace for sponsoring today's video. I'm sure we've all seen the breathtaking imagery from the Hubble Space Telescope of beautiful and Thanks to Squarespace for sponsoring today's video. I'm sure we've all seen the breathtaking imagery from the Hubble Space Telescope of beautiful and multicolored nebula. It almost seems as if a contemporary artist flicked different colors onto a canvas. But this isn't just a pretty picture. What you are seeing here are actual structures, tens to thousands of light years across. But how are these images so colorful? Does it really appear like that in real life? To answer this question, let's give you some context. Nebula may appear solid or maybe even like clouds, but that is far from reality. Nebula are extremely diffuse gas clouds. On average, you may get about 10 to 100 particles per cubic centimeter. This is far less than any artificial vacuum produced on Earth. To give you a sense of how little that really is, a comparable cubic centimeter at sea level on Earth contains 10 quintillion particles. That's 10 to the power of 19 particles. On the other hand, if you were to have a nebula the size of Earth, it may only have a total mass of a few kilograms. Orion, perhaps the brightest nebula in our sky, is just about bright enough to be seen with the naked eye on a clear night. However, nebula can be a lot brighter too. If the Tarantula Nebula, found in the Large Magellanic Cloud, was as close to us as the Orion Nebula is, it would even be visible during the day. But if nebula are so sparse, how can we see them at all? It's important to remember the scales that are at play here. While nebulae are sparse, they are also massive. H2 regions, which are a specific type of nebula, are known as stellar nurseries. These massive clouds can collapse and coalesce, and when they do, they form stars. A single nebula can contain enough mass to create hundreds to thousands of stars, and it is actually these newly formed stars that light up the gas in a nebula. Solar radiation shoots away from stars within a nebula, ionizing the nebula's particles, which releases this energy at a specific light wavelength. This means H2 regions are known as something called emission nebula, because ionized atoms within are emitting their own light. The process happening in an emission nebula is comparable to what happens in a neon light, where electricity ionizes neon within the bulb, causing it to light up. However, in a nebula, it's not neon that lights up. In fact, in the Hubble images, each color shows a different ionized atom. Unfortunately though, I can't tell you a blanket rule for colors in Hubble images. So, while in this image of the Carina Nebula, reds correspond to sulfur atoms, greens to hydrogen, and blues to oxygen, in this image of the Swan Nebula, blues correspond to visible light blues, greens to oxygen, and reds to infrared and hydrogen. That's because of the way Hubble takes its photos. Hubble is primarily a visible light telescope, but its optical range does also extend into the ultraviolet and infrared. When scientists look at a nebula, they often want to see what it is made of, so will photograph the object using specific filters. So, say they want to see hydrogen in a nebula. They will image the nebula using a filter that lets light being emitted along 658 nanometer wavelengths through, or in other words, the emission band of hydrogen. After that, they are left with a black and white image. Then they may decide to image the nebula again, this time looking for sulfur along 672 nanometer wavelengths. And then again, looking for oxygen along 501 nanometer wavelengths. Scientists then assign colors to each of these different photos and combine them together to produce the colors you see here. As you browse Hubble images on their website, you can see for yourself what the colors have been assigned to by looking to see what wavelengths of light were used. For Hubble images of nebula, they are pretty much always a false color. However, Hubble does also take natural color images too. The Sombrero Galaxy, for instance, had 3 different images taken in blue, red, and green, or RGB. So the colors you see here are how you would see this galaxy, were it bright enough for you to see it. So, if Hubble's images of nebula are false color, what would they really look like to us? Generally speaking, a lot more red. The European Southern Observatory also looks at a lot of the same objects Hubble does, although often using different color filters. Going back to the Carina Nebula, on ESO's website, we see that the color bands are RGB, or natural light, so we know that what we are seeing here is the Carina Nebula as we would see it. Here's ESO's version of Orion, except this time with ultraviolet and hydrogen overlaid on top of natural colors. So far we've only discussed the most famous nebula type, H2 regions or emission nebula. However, it is worth mentioning that there are a few other types of nebula too. You also have reflection nebula, where the energy from stars isn't enough to ionize the nebula. Instead, it reflects or scatters the starlight, meaning these nebula tend to have similar frequency spectrums to nearby stars, often appearing slightly bluish. You also have dark nebula, or nebula with no stars around them to illuminate them. These almost appear pitch black. All in all, nebula are not as colourful as you may have initially thought, but to me that doesn't make them any less interesting. Looking through these filters means we can understand a lot more about nebula than we otherwise could have, and they do make for beautiful images. Thanks again to Squarespace for sponsoring this video. Squarespace gives people a powerful and beautiful online.
So we talked about bright nebula and dark nebula. Dark nebula are ones that are not lit up in some way and are blocking light from behind them. bright nebula are lit up. They come in two basic types: emission nebula, where energy from nearby stars ionize the hydrogen gas, resulting in fluorescence. So emission nebula, the nebula itself is glowing. The gas inside it is excited, so they tend to be red. And reflection nebula is where dust within the nebula reflects and scatters starlight, giving off a characteristic blue color, because the stars around nebula tend to be very young, hot, and blue. Well, the bright stars are. So here's the Great Nebula in Orion, which is an emission nebula. And dark nebula produced by the obstruction of a relatively dense cloud of interstellar dust. They're visible as relatively dark areas as they're framed against some type of light emitting region behind them. And the most famous of the dark nebula is located in the constellation Orion. It appears like the head of a horse, backlit by a bright emission nebula. So it's just a dark cloud of dust in front of the glowing cloud of gas. This is the Horsehead Nebula. So this is the backlit emission nebula. This is the dark cloud of dust getting in the way. And to look inside nebulae and understand like stars being born, we generally use infrared telescopes because they can penetrate through the dust. They aren't blocked by, infrared light is not easily blocked by the dust because the particles are too small for that. So let's go over the general evolution of a low mass star, how it starts. So stars begin to form as interstellar material, mostly hydrogen, gathers together via accretion. This can be due to a few different reasons. The material is gravitationally attracted to itself. It can be pushed together by radiation pressure from nearby stars or shock waves from exploding stars in the vicinity. These can cause areas to become denser and start to collapse under their own gravity. And as this lump of material condenses and collapses under its own gravity, you get a protostar, which is just a ball of hot gas. The star is getting hotter and hotter as all the material is falling inwards and rubbing against each other with friction and heating up. And if you take a gas and you compress it, it gets hotter. Same thing is happening here. So it's being compressed by gravity, it's getting hotter. So as the protostar continues to condense, the temperature continues to rise. And once the core of the star gets hot enough, it will stop being a protostar because fusion will begin. Once it gets hot enough and dense enough, fusion will start, where hydrogen is converted into helium. And that is when you have a star. That is the point where a star is born. That's the official difference between a protostar and a star, is when fusion starts. So this is the reaction for fusion. 4 hydrogen nuclei combine to form 1 helium nuclei with 2 positrons, 2 neutrinos, and 2 gamma rays. And some energy in the form of, stuff moving around quickly. And the positrons are going to annihilate and turn into energy, and the gamma rays are going to run into, that's just light. And the neutrinos fly out free on their own, and then they're passing through you right now. Thousands and thousands of them are passing through you right now. Because nothing really stops neutrinos. Which is why neutrino detectors are these giant tanks of water in the bottoms of mines. You detect like individual events. So this is a short video going over the process of the birth of a star. So again, it's just this cloud of gas and dust collapsing, and we talked about this when we talked about how the solar system formed, but it's collapsing under its own gravity, spinning faster and faster, and the center is heating up and eventually becomes a star.
all you need to make a star is hydrogen, gravity, and time.
Gravity pulls the dust and gas into a giant, swirling vortex.
Gravity brings matter together. And when you bring matter together and you squeeze things into smaller spaces, they necessarily heat up. It's a simple law of chemistry. You compress something, you drive the temperature up.
Over hundreds of thousands of years, the cloud gets thicker and forms a giant spinning disk bigger than our entire solar system. At its center, gravity crushes the gas into a super dense, super hot ball. Pressure builds until huge jets of gas burst out from the center.
That really shows you how violent a process star formation is. These jets are many light years across. Something is literally accelerating material very fast across unimaginable distances.
Gravity keeps the pressure on, sucking in gas and dust particles that smash into each other, generating more and more heat. Over the next 500,000 years, the young star gets smaller, brighter, and hotter. Temperatures at its core reach 15 million degrees. Only at that mind-boggling temperature can atoms of gas begin to fuse together, releasing massive amounts of energy. And just like that, a star is born.
So at that moment, when thermonuclear fusion begins, that is when a star is born. And then it will move onto the HR main sequence in a position that's determined by its temperature and brightness, and both of those are dependent on the star's mass. So again, more massive stars are at the upper left of the HR sequence. They're bright, they're hot. They're, while less massive stars are at the lower right of the HR sequence, they're cool and dim. And it also turns out, so starts as a cloud of interstellar gases and dust, forms a protostar, is compressed until it ends up on the main sequence, stays on the main sequence for a long time, and then leaves, becomes a giant, possibly a variable star, throws off its outer layers as a planetary nebula, and leaves behind a white dwarf. That's for a smaller star. A larger star will evolve a little bit differently. So as a star continues to fuse hydrogen into helium, it remains on the main sequence. And the period that it remains on the main sequence varies widely. And it again depends on the mass of the star. The main thing that determines what happens with a star is how massive it is. So a low mass star like our sun will stick on the main sequence for around 10 billion years. A very low mass star can stay on the main sequence for trillions of years. While high mass stars burn their fuel faster. So the more massive the star is, the hotter its core is, the faster it burns up its fuel. And only remain on the main sequence for the highest mass stars only remain on the main sequence for a few million years. So the bigger star is, the brighter it burns, the shorter it lives. So as the hydrogen in the helium converts to the hydrogen in the core converts to helium, the core starts to contract and heat up even more. And when you get to a point where you basically run out of hydrogen in the core, then the extra heat from this contracting core causes the hydrogen in the surrounding layer of the surrounding shell to heat up, which causes it to start to fuse, which in turn destabilizes the star's hydrostatic equilibrium, resulting in the star expanding to form a red giant. So a red giant actually forms when the core of the star shrinks. The layer above it starts to fuse, and that overheats the insides and causes the outside layers to expand and cool. So at this point, when the star expands, it enters the red giant phase and moves off the main sequence. And that's the beginning of the end for a star. So when our sun moves into its red giant phase, that'll be something like 5 billion years from now. It'll swell, engulf Mercury and Venus, and maybe also Earth. There is debate about exactly how big our sun will get, because we don't, we don't exactly know how much material it'll lose on the way there and stuff like that, and exactly how big it'll get. And the core of a red giant eventually becomes so hot, it's something like the sun, that high helium can fuse into carbon, and maybe will, depending again on the mass of the star, will create elements up to neon. And so this is this process of nucleosynthesis, which is the creation of elemental nuclei in stars. And basically every element heavier than helium, so every element on the periodic table past helium, comes from stars. Now, in high mass stars, red supergiants, you can build up more layers and the core can get even hotter. And you can actually achieve nucleosynthesis all the way up to iron. And iron is the most stable nucleus out there. And at this point, you can't get any more energy from fusion once you reach iron. If you fuse iron, it costs energy. So once the core becomes iron, it doesn't generate heat anymore. It stops pushing outwards. It collapses quickly and dramatically as it implodes. A bunch of gravity starts taking over. It's big enough that gravity is strong enough to force electrons into protons to form neutrons. And this actually causes the outer layers to fall in and basically bounce off and explode, and that's a supernova. So for a star in the red giant phase, variations will occur in temperature and brightness during the red giant phase. This is a variable star. So a star can become a variable star, and its position on the HR diagram moves left. Certain types of variable stars are incredibly useful because it turns out the rate at which they vary corresponds to how bright they are. And that is incredibly useful for measuring distance. And then after the variable star stage, the star becomes very unstable. The outer layers blow off, forming what's called a planetary nebula, which is called this because it looks sort of like a solar system, because you get a bright white dwarf in the center and circular clouds of gas around it. Planetary nebulae have nothing to do with planets, but early fuzzy photographs of planetary nebula reminded astronomers of an evolving solar system. And this expelled material drifts off into space. Planetary nebulae don't last very long. And this provides material for future generations. So here's an example of a planetary nebula, the Eskimo Nebula. And in the center, you can see the white dwarf, which is the core of the star, while this all is the outer layers that were blown off. So after the formation of a planetary nebula, the remaining core that stays behind is called a white dwarf. So in a white dwarf is just a ball of stuff that is compressed until quantum mechanics says it can't get any more squished. So thermonuclear fusion isn't happening in a white dwarf. It will just slowly cool by radiating its energy into space. However, a white dwarf is very small and very dense. So it takes a very long time to slowly radiate away all its energy. And because they're very small, they're not very bright. So they fall low on the HR diagram. But they're incredibly dense. So what happens is that the matter in them compresses until it is held up by the quantum mechanical effect called degeneracy pressure, which is basically when you have electrons, two electrons can't be doing the same thing in the same place. And that creates a pressure that holds up the size of the white dwarf. And so a single teaspoon of matter in a white dwarf could weigh 5 tons. So a white dwarf has a mass, will often have a mass around the size of the sun. So a white dwarf with a mass around the size of the sun would, around the mass of the sun, would have a size of around the size of the Earth. Super dense. So here's a short video about the weirdness of white dwarfs.
The universe is dotted with a tremendous number of stars, each shining brightly from the energy of nuclear fusion. At any given moment, new stars are born, while others begin to die. The fate of a dying star depends on its mass. The largest stars will become neutron stars, or black holes. But the vast majority of the stars will become hot balls of glowing matter that will shine for billions of years as they slowly cool down and disappear from view. These are white dwarfs. Stars shine because of nuclear fusion. It takes a lot of energy to fuse two atoms together. This is why large bodies like stars fuse matter, while smaller objects like planets do not. Stars are so large that gravity squeezes their matter together tightly enough for fusion to occur. This fusion mostly occurs in the core of the star, but at times it can also take place in layers surrounding the core called shells. As the star ages, fusion happens in different parts of the star and produces different elements. This process is called stellar evolution, and the path it takes depends on the star's initial mass. During this process, the size, temperature, and composition change. But for every star, a point is reached where the pull of gravity is no longer strong enough to keep fusion going. For most stars, once fusion stops, that's it. Because fusion is no longer generating an outward pressure, the star contracts under the force of gravity to about the size of the Earth. But the lights don't go out right away. All that matter is still extremely hot, and hot things glow. So now you have a small ball of white hot matter floating in cold space. We call this a white dwarf. As the years pass, white dwarfs cool down and begin to dim. After all, space is very cold, close to absolute zero. So how long do you think it will take the white dwarf to cool down to the point that it goes dark? 1 year? 1,000 years? 1,000,000 years? It's believed it will take trillions of years for white dwarfs to stop glowing. That's longer than the current age of the universe. But one day, somewhere in space, the lights will go out in a white dwarf. At that point, all that's left is a dead ball of dark matter, which we call a black dwarf. Although white dwarfs are small compared to burning stars, they're still quite massive. Their mass can be as high as 1.4 solar masses, a value called the Chandrasekhar limit. Because of their large mass, gravity very tightly compresses the stellar matter. But at some point, you run up against the Pauli exclusion principle. This idea from quantum mechanics says basically that two identical particles cannot occupy the same place at the same time. For white dwarfs, the pressure from gravity has stripped all the electrons from the atoms. Gravity then packs the electrons so closely together that the Pauli exclusion principle kicks in and stops the white dwarf from shrinking any further. This is called the degenerate electron pressure. White dwarfs are about the size of an Earth-like planet and shine with only a fraction of the brightness of a star. So how do you find and observe them? One way is to look for stars with an unexplained back and forth motion. This suggests a massive companion. If you can't see the companion, it's probably a black hole. But oftentimes, telescopes are able to see a small, dim neighbor, a white dwarf. In fact, the brightest star in the night sky, Sirius, has a white dwarf companion which we call Sirius B. There's another way to find white dwarfs, and it's due to a curious phenomenon which occurs near the end for some stars. Earlier, we mentioned that fusion can occur not just in the core, but in the shells around the core. When a star begins to die, fusion may stop in the core. That's because the core is now made of heavier elements and there isn't a strong enough compression to fuse them. But a shell of helium may start to burn in an event called a helium shell flash. This creates a shock wave called a thermal pulse, which blows a lot of the star's matter into space. This expanding sphere of matter glows from the star, creating a beautiful display called a planetary nebula. The name is a bit misleading, has nothing to do with planets. The name was chosen hundreds of years ago by William Herschel because he thought they looked like planets. Regardless of the name, when you see a planetary nebula in space, there's a good chance you'll find a white dwarf in the center. It is estimated that more than 90% of the stars in our galaxy will end up as white dwarfs. So as time passes and the billions and billions of stars in the Milky Way begin to burn out and fade from view, you can rest assured that for more than 1 trillion years, you'll still be able to find a warm, glowing white dwarf to call home until you can find a more permanent location. While white dwarfs will shine long after this video is over, this button has only a few seconds left to live.
So Sirius A is an A-class main sequence star. And here, this little dot down here, that's Sirius B. It's a white dwarf companion. So yeah, white dwarfs, balls of matter held up by degeneracy pressure. They have an upper limited size of around 1.4 stellar masses. At that point, gravity will overcome degeneracy pressure. Has to do with relativity. And if the core of a star is bigger than that amount, when it collapses, it can form a neutron star, where there's enough gravity that the electrons merge with the protons in the atoms and form neutrons. And so you have a ball that is basically a nucleus. So this is something, a neutron star is somewhere between 1.4 and about 3 solar masses, and it's about the size of a city. It's incredibly dense. But you can also have what are called brown dwarfs. Brown dwarfs are what happens if the starting material to form a star just isn't quite big enough. Yeah, what if the protostar never gets hot enough to sustain nuclear fusion because it's too small? And in this situation, a protostar doesn't progress to the star phase. You get a failed star or a brown dwarf. So brown dwarf stars are very dim. They're sort of the stage in between planets and stars. There's a technical definition about like what makes it a planet and what makes it a brown dwarf. Brown dwarfs can have certain types of fusion, but not actual hydrogen fusion. And the first brown dwarf was not discovered until 1996. And that is Gliese 229b. And about 600 brown dwarfs have now been found. But they're all, small, dim stars. And the evolution of a low mass star goes protostar, star, giant, variable, or, red giant, planetary nebula, white dwarf. And you can get something called a nova. I don't know if there was supposed to be a nova, but there's a predicted nova, but I don't know if it ever actually happened because it was not, I have to check. But a nova is a white dwarf that temporarily and suddenly increases in brightness. It's called a nova because often it went from not being visible to being visible. So it was a new star. And novae result from actually just nuclear explosions on the surface of a white dwarf. So this is what happens is material from a partner star. So most stars are binaries. So if that partner star can lose material to the white dwarf, that material settles on the white dwarf, heats up, undergoes thermonuclear fusion, and basically explodes, causing a sudden increase in brightness. That's a nova. And so this can happen over and over again. So there's one that's predicted to happen, or was predicted to happen right around now, because we had some understanding of the cycle that that star went through. Now, there's also a supernova. So a nova is an explosion on a star on the surface of a white dwarf. A supernova is the gigantic and catastrophic explosion of a star, where large amounts of material and radiation get thrown outwards. Supernova are when stars blow up. And there are two types. Type 1 supernova occur when a white dwarf, we talked about how a white dwarf can accumulate matter on it and undergo novae. If that white dwarf gets enough matter on it to become larger than the Chandrasekhar limit, it collapses and heats up and gets hot enough that the carbon and oxygen it's made of will fuse, and the whole thing goes off like a bomb, and nothing remains. That's a type 1 supernova. It is a white dwarf getting enough matter on it to collapse, start to collapse, get hot enough for fusion to occur for all the material that it is made of, which is mostly carbon, and explode violently. And then type 2 supernovae result from the collapse of the iron core of a red supergiant. This leaves behind either a neutron star or a black hole made of the core, while the outer layers are blown off in a violent explosion. Type 1 and type 2 supernovae have different spectral signatures. They also have the way their brightness varies over time is different as well. So type 1 supernovae don't have hydrogen spectra, and they don't emit radio waves, because they're just a whole bunch of carbon exploding as a fusion bomb. Well, type 2 supernovae do display hydrogen spectral lines because there's a star in the way of that explosion. The outer layers of that star are still mostly hydrogen and do emit radio waves because the process is different. And supernovae leave behind remnants. So this is the Crab Nebula. This is the remnant of a type 2 supernova. In the middle of this, there is a neutron star. That's the remnant of the core of the star that exploded to form the Crab Nebula. And this happened about 1,000 years ago. Like the actual supernova that created the Crab Nebula was observed and recorded. So the Crab Nebula is the best known and one of the fewer than 10 supernovae that have been recorded in the Milky Way galaxy. The supernova that resulted in the Crab Nebula was reported in Chinese and Japanese records around 1054. And during the first 2 weeks of the supernova's appearance, the night sky was bright enough to read by. Incredibly bright, dramatic thing. So this is the Crab Nebula. And in the center of the Crab Nebula, there's what's called a pulsar. which is the rapidly spinning neutron star that pulses because it's emitting beams of radiation that sweep around as it spins. And the supernova explosions are how we get all elements heavier than iron. I mean, it's a little more complicated than that in reality, but basically they're a necessary step in how we get all elements heavier than iron. So the energy and neutrons emitted during a supernova explosion results in the nucleosynthesis of elements that are heavier than iron. Basically, yeah, because you can't fuse past iron and get energy out. To get past iron, you have to throw energy in. Well, you have a massive explosion emitting tons of energy. That'll do it. And so other than hydrogen and helium, all the elements up to iron are thought to be made more or less during normal fusion processes in stars of various masses. Again, the actual details are a little more complicated. So things like, it turns out there's a few elements that are skipped over. So like lithium, part of why lithium is really rare is because it turns out to get lithium, make more lithium needs supernova explosions. And elements past iron are thought to be generated exclusively during supernova explosions. Again, the actual process is a bit more complex and has some additional steps to create everything, but supernovas are involved. And when the nuclear fuel interior of a red supergiant is depleted, the core is full of iron and it collapses. And this can collapse, and this will collapse to form, if it's not too big, a small neutron star. So if the core is less than about 3 solar masses, it will form a neutron star. And a neutron star is about 20 kilometers in diameter. It's about the size of, a city. Comparable in size to like Manhattan. And again, the mass is more than 1.4 solar masses, between 1.4 and 3 solar masses, compressed to the size of a city. The outer layers also collapse. They bounce off the rigid inner core. They expand into space, and that's the supernova. And it leaves behind this small core that is a neutron star. Again, it's a little more complicated than that, but basically these layers get superheated by neutrinos of all things, and get blown off. But yeah, so you have this ball that was iron, but is actually like one giant atomic nucleus that's a few solar masses. It's made of something called nuclear pasta, which is crazy. And so the name neutron star comes from the fact that the gravitational force is strong enough to squeeze the electrons and protons together so that they turn into neutrons. And neutron stars are the densest material in the universe. They're on the order of 1 billion tons per teaspoon. And they're super weird. They have intense magnetic fields. They're super dense. They spin really fast because they were this big thing that collapsed. So they're spinning really fast. And they can emit beams of radiation because of the intense magnetic fields. And those beams can sweep along and because they're spinning really fast, and they create pulses, or the beams of radiation points in our direction, and that creates what's called a pulsar. So for example, the pulsar in the Crab Nebula pulses about 30 times a second. So here's a short video about neutron stars and what would happen if you got too close to them, where you would be violently deconstructed by tidal force.
A neutron star is the densest body we know of in astrophysics besides a black hole. So if you somehow had a little stone-sized piece of neutron star matter, it would weigh 100 million metric tons, and it would immediately fall right through your hand.
Because the neutron star is so dense, it generates an intense gravitational field.
It is really hard to exaggerate how dramatic and dangerous a neutron star is. The gravity is so intense it would actually bend light around it. You would see all these kind of weird shimmering effects.
Dazzling, but deadly. No astronaut will ever be able to approach a neutron star. But if you're an armchair traveler and want to find out what would happen, let's send a galactic crash test dummy. We'll call him Chuck. As Chuck nears the neutron star, its gravitational grip is doing very bad things.
The gravity is pulling on him so hard that he is accelerating all the way down to the surface. He'll be moving at very roughly 1/2 to 2/3 of the speed of light.
The neutron star's gravity is 200 billion times stronger than on Earth. Around 150 miles above the surface, it starts to pull on Chuck's limbs in a distinctly unpleasant way.
As you get closer and closer to a neutron star, we were told to think that it would be this elegant spaghettification where you would get longer like a piece of spaghetti. But in reality, you're gonna get ripped to shreds.
Think about what you're really gonna experience. Think about, first, all your joints dislocated in your body. Your skin getting ripped off of your body, your bones being pulled apart, your organs being pulled apart.
Within a blink of an eye, our dummy is just a thin stream of atoms hurtling towards the star.
Those atoms will eventually fall down onto the neutron star. And unfortunately, the violence doesn't stop there.
What's left of Chuck hits the surface, triggering a huge burst of energy.
So we're talking about 100,000 miles per second. That's an impact. He's going to hit so hard that the amount of energy released is just huge. It would completely dwarf the entire arsenal of nuclear weapons on our planet.
Anything and anyone that ventures too close to a neutron star is destined for this catastrophic end.
So, any angular momentum a star had, that the original star had, has to be maintained. So therefore, the small size of a neutron star dictates it has to spin really, really fast. And neutron stars also have very strong magnetic fields, some of the strongest in the universe. And those magnetic fields aren't necessarily aligned with the direction of the spinning. So you get beams of radio waves being emitted. So a pulsar can emit radio waves that are detected on Earth in regular pulses due to its rapid rotation. And every pulsar has a constant period. They run because they're spinning at a constant rate. We see a pulsing at a regular rate. And it can be between 0.03 and 4 seconds is pretty normal. There are some very, very fast ones. But in general, they're between about 0.03 and 4 seconds. So for example, the Crab Nebula is a pretty normal one. It's 30 times a second. And over long periods of time, pulsars do in fact slow down because they're emitting energy by radiating it away and through gravity waves and stuff. But they're interpreted to have a magnetic axis, which is tilted relative to the rotational axis. And they're sending out beams of material or particles that cause these radio waves. So there's this magnetic axis, there's a beam of stuff, that's radiation coming out, and that's what we see, and it rotates around. You can actually observe some pulsars outside of the radio spectrum. We just detected them first in radio waves. Like the one in the Crab Nebula, it lights up the nebula. So you can actually observe it in the visible. And as the neutron star rotates, the radiation beam caused by the magnetic field hits the Earth periodically. And on Earth, the radiation beam is detected as pulses. but it's actually the beam sweeping by. One of the ways we detect these things are with stuff like the Very Large Array in New Mexico, which is an array of radio telescopes. These are designed to detect radio wave images of distant celestial objects. And the pulsar at the center of the Crab Nebula pulses about 30 times a second. And it also, this nebula emits pulses of visible light because the nebula gets excited by the stuff being thrown off by the pulsar. Now, if an object is too big, if the core of a star is too big, you get what's called a black hole. So a black hole is an object where the escape velocity is equal to or greater than the speed of light. This is the point where gravity wins. And not even light can escape the surface of a black hole. So black holes are thought to result from a supernova explosion when the core remaining is more than 3 times the mass of the sun. And the star's matter will continue to condense down. It's thought the star's matter will continue to condense down into an extremely small point known as a singularity. But we don't really know, because basically black holes are just where we say gravity wins, here's what the math says if gravity could win. We know they exist, but we can't see anything past the point of no return, the event horizon. So we assume there's a singularity in the center of a black hole, but we could be wrong. It would look exactly the same if it was just a little bit smaller than the event horizon. Because that's the point of no return.
Black holes are among the most fascinating objects in our universe, and also the most mysterious. A black hole is a region in space where the force of gravity is so strong, not even light, the fastest known entity in our universe, can escape. The boundary of a black hole is called the event horizon, a point of no return, beyond which we truly cannot see. When something crosses the event horizon, it collapses into the black hole's singularity, an infinitely small, infinitely dense point where space, time, and the laws of physics no longer apply. Scientists have theorized several different types of black holes, with stellar and supermassive black holes being the most common. Stellar black holes form when massive stars die and collapse. They're roughly 10 to 20 times the mass of our sun and scattered throughout the universe. There could be millions of these stellar black holes in the Milky Way alone. Supermassive black holes are giants by comparison, measuring millions, even billions of times more massive than our sun. Scientists can only guess how they form, but we do know they exist at the center of just about every large galaxy, including our own. Sagittarius A, the supermassive black hole at the center of the Milky Way, has a mass of roughly 4 million suns and has a diameter about the distance between the Earth and our sun. Because black holes are invisible, the only way for scientists to detect and study them is to observe their effect on nearby matter. This includes accretion disks, a disk of particles that form when gases and dust fall toward a black hole, and quasars, jets of particles that blast out of supermassive black holes. Black holes remained largely unknown until the 20th century. In 1916, using Einstein's general theory of relativity, a German physicist named Karl Schwarzschild calculated that any mass could become a black hole if it were compressed tightly enough. But it wasn't until 1971 when theory became reality. Astronomers studying the constellation Cygnus discovered the first black hole. An untold number of black holes are scattered throughout the universe, constantly warping space and time, altering entire galaxies, and endlessly inspiring both scientists and our collective imagination.
So black holes are super weird, but they're also kind of super simple because they're just the point where gravity wins. And it turns out you can describe a black hole with just 3 numbers. Its mass, its charge, and its angular momentum. So the way you detect a black hole, well, you can't see it. It's not emitting any light because the event horizon of a black hole is a one-way boundary. Anything can enter, but nothing can escape. But if nothing can escape from a black hole, how can it be detected? Well, it's still got gravity, and that's affecting the area around it. And it turns out stuff falling into a black hole sure does emit light and can be very bright. And in fact, some of the brightest things in the universe are stuff falling into a black hole. So detection of X-rays being emitted by material falling into a black hole in the vicinity of a black hole. So captured gases just around outside the event horizon, as they fall inwards, rub against each other, they heat up, they emit X-rays and form an accretion disk. We also see these disks of material. So here is an example of a class O star and a black hole. So material is going from the class O star to the black hole, and as it falls in, it speeds up. You get a friction and it forms an accretion disk and it emits X-rays. And that's Cygnus XY. And these X-rays that are being generated are apparently due to an accretion disk of gases being captured by the black hole. And we can take an image of a black hole, it turns out. So this is the image of the supermassive black hole at the center of the galaxy M83. I may not be remembering the number right. You can see the event horizon in the center, and what we see glowing around it is the accretion disk. So this was taken by the Event Horizon Telescope, which has also imaged the supermassive black hole at the center of our own galaxy. The first one they did was of this much larger black hole in M83, I believe, because it was easier to see. There was less stuff in the way. So let's talk about the differences between high mass and low mass stars. High mass stars and low mass stars initially form in very similar manners. High mass stars are hotter and brighter than low mass stars. They move on to the main sequence at higher points. They don't live as long. They don't stay in the main sequence as long as low mass stars due to their higher rate of thermonuclear fusion. They burn through their fuel a lot faster. And when a high mass star moves off the main sequence, they become a red supergiant, and they eventually explode as a type 2 supernovae. Most of the material gets scattered into space, and that leaves behind either a neutron star or a black hole, depending on how big the star was initially. If the core is bigger than 3 solar masses, it's a black hole. If it's between one, if it's less than 3, you get a neutron star. And in general, we learned the initial mass that a celestial object acquires during its formation basically determines what happens for the rest of its life. But the final mass left over after any stellar material gets ejected is what's the conclusive determinant. But that final mass is basically determined by the initial mass. So if the final mass left over is less than 0.01 solar masses, that's a planet or a moon. If it's 0.01 to 0.07 solar masses, that's a brown dwarf. If the remaining bit is 0.08 to 1.4 solar masses, that's a white dwarf. If it's about 1.5 to 3 solar masses, that's a neutron star. And if it's greater than 3 solar masses, that's a black hole. This is not the starting mass of the star. It's the ending mass of what remains. The starting mass for stuff that can become a white dwarf the line between white dwarf and neutron star is around tens-ish solar masses. And the line between neutron star and black hole for the starting mass is around 20-ish, if I remember correctly. And that is all I wanted to cover for today. So have a nice day. Lab today is for makeup. If you have any labs you need to make up, if you have any late labs you need to turn in, you can turn them in. If you have the Eclipse lab, it's due today, but I think most of you already turned that in. Otherwise, I'll see you on Thursday. Have a nice day. Yep. And yeah. Have a good day. You too.